Hello. Today I'm going to mention about the Spectre Attack. On the 1st of June 2017, researchers working for Google's Project Zero found two major security flaws in modern processors. These flaws allow any program to read sensitive information from memory. These bugs are called Spectra and Meltdown. And because of they're so sensitive, Google decided to keep it a secret until the vendors had come up with workaround that would protect our information. So, for a while, chip makers and architecture designer companies were in a fight to keep increasing the clock speeds. They, however, reached a ceiling when they hit the 3D 4 GHz range. Increasing it further was almost impossible, so instead chip makers had to get creative and they come up with something called speculative execution. Basically, it means the processor which will guess what the outcome of the instruction will be and execute all the subsequent steps in the background. What we call it as branch prediction. So let's take a look at how these bugs are working. Suppose that we have a code like this, and we have an if-else statement, just like this one. If the condition 1 is correct, then assign the memory 1's index into the integer a. If not, for the second if statement, condition 2, assign the address 2 into the integer a. To make the system work faster, we predict the branch as assuming the condition is right, and we fetch the data before the condition is satisfied, assuming that it will be true. But to make that assumption, we have to get some correct conditions before. Suppose imagine that you have a for loop that have multiple values, and you are fetching the one after another, and then you are predicting to fetch the next one. So in order to provide this prediction to the system, to the branch predictor, we have to make some true conditions for the first. But this causing the misfetch for the case that condition is not satisfied. Even though the registers turn execution as invalid, the fetched value remains in the cache memory as just like here. This is the main memory, and this is the one that we fetched into the cache memory. Even though this was cancelled, even this became something invalid, it remains in here. So after that, since cache memory is used in multi-processor systems, and this causes a problem in this case. So by reminding that we have the register value in the cache memory from the previous slide. So the cache memory is shared memory and the multiple programs, which is causing programs to reach the register values by using the access time depending on the latencies of information. It is possible to define whether if it is on the cache or on memory. So we call this a side channel effect. So to sum up, to understand whether if the data is on the cache or not, we compare the access times. So if it is lower than the cache hit threshold, then we can understand that it is in the cache. So according to understand that, um, we will let's take a look at Spectra attack mechanism. Branch predictor works according to the previous executions. In this code, for example, they're giving x values lower than array 1, since for couple times to make the prediction. It's just like I mentioned. As the next value will be true, so that they can get the unreachable data of another program to reach cache memory. But it doesn't show the data directly. So it became invalid, but it still remains in the cache. They can read it by side channel attack. So those who makes the attack scanning all the elements of the array by their address and compare if their fetching time is lower than the cache threshold, cache hit threshold, to recover the one that fetched to the cache. It's also the one they wanted to reach up for the most of the time. To give a and here this is an illustration of imagine that you have an array and you have the size of it, and you are making a scan, kind of a scan, and when you hit the element that lower than the hit threshold, then you can be sure that it is the one that fetched to the cache memory. And to give a concrete example, a website could use Spectre to read the context of another browser's tab, one where you might be logged into your bank account. So it is pretty important, actually. And that is how the Spectre attack works. And this becomes an even bigger problem in professional situations. Public clouds like AWS, Google Cloud, and Microsoft Azure are rushing to implement safeguards against Spectre and Meltdown. If left unpatched, it would allow one customer's virtual machine to steal data from another customer's virtual machine. Spectra is more difficult to patch compared to the Meltdown. That's also why they named Spectra. Patching processor isn't possible because we can't change hardware that has already shipped. Instead, we have to mitigate it with some software updates. Browsers like Firefox and Chrome are also offering patches to mitigate the risk of websites stealing sensitive information. Thanks for listening. Have a good one.